Yeah, hi everyone. Welcome to Probability and Statistics Part 1. Um, so, in this class, we will be looking at all of this. It looks a lot and it is a lot, but yeah, we'll try to cover as much as possible. So, we'll look at um, basically um, what an experiment is, what a trial is, what an outcome is, again all with respect to probability, right? Then what is an outcome? Then what is a fair or unbiased setup, sample space, event space? How do we calculate the probability, right? Set operations. Then what is an empty set? Types of events, and then we'll do some kind of analysis on a data set with the stuff we have learned above. So that will be the agenda. Give me a second, this formatting is slightly messed up. Okay. Yeah, I guess nothing I can do about it. No. Okay, I guess that's all. There's nothing we can do. Okay, yeah. So, okay, now the first topic is an experiment. So basically, when we are trying to perform an action or a set of actions, and we are defining the outcomes properly for like all possible outcomes that this action or a set of actions that we take, when we define all possible outcomes, that entire system is called an experiment. So let's see. So what is an action? So it can be anything like again I'm giving very common example, something like a coin toss, right? So if I flip a coin, that is one action, right? And the outcome is either a head or a tail. The outcome, or rather the result, is either a head or a tail. If I take another example, again a very common one is a dice roll, right? We have a bunch of dice, and okay, in this case we are not doing dice, it's basically a die roll. If I'm not wrong, that's the singular, a single die. So when you roll a die, you get numbers ranging from 1 to 6, right? A standard fair die. Again, a fair coin toss. We'll look at what fair means in detail, but fair means basically it's a standard coin. Like it's not rigged in any way. It's not a cheat coin. It's like a fair coin. Let's put it that way. I'll talk about what fair means in detail. In essence, it's a proper coin, and it's also a proper die. It's not like some strange messed up die where one of the sides is kind of messed up or something like that. And if I have to give another example, I'll stick to very common examples because that will be easier to operate. But an action can be anything. Like maybe you're throwing a water bottle and you're measuring how far it went, or maybe you are I don't know, maybe you're hitting a punching bag and then you're seeing how like you're measuring your strength or something like that. The outcome, I don't know if you see the punching machines, if you punch the bag, you'll see that there's a number that tests your power, right? That could also be an action. And so coming back to the other experiment, again a very common one. So coin toss, die roll, and even selecting a card from a 52 standard card deck, like 52 cards, the poker cards, right? You have, and if I select a card, yeah, right, you might get either a, you might get a, give me a second. Yeah, you might get one of either a red card or a black card, and within these you might get a spade or a diamond, right, or a club or a heart, and then you might even get a face card as well, right, like a jack or a queen or a king, and you have all these equivalents here as well. So all of this, like drawing a card, throwing a dice, flipping a coin, all of this is considered an experiment. Like you can have this one action as an experiment, or you can have multiple actions. You can say just throwing a coin and checking my outcomes head or tail is one experiment, or you can say I toss a coin, like coin toss and dice roll or die roll. These both actions combined can be one single experiment. Or I can have coin toss plus dice roll plus select card. These three actions combined can be one experiment. Like that, you can have n number of actions, right? All of these are considered one experiment. Now, what is not an experiment is basically when your outcomes are not defined. If you are, suppose, I don't know, in scientific sense, if you are, say, looking at the night sky and you are observing and you are gathering information, that's not experiment. Basically, you need to have your outcomes ready. Like if you are performing an action, then you should know that I will get X, Y, Z set of possible outcomes, right? You must know all set of outcomes beforehand for it to be considered as an experiment, at least in probability theory. Only then it is. Otherwise, if you are still exploring and you are trying to find something new, that is not considered an experiment. The properties basically are you should have your action, your particular set of actions, and you should have your outcomes ready. This is like the criteria for it to be considered an experiment. Again, we have seen the examples, right? Which is basically coin toss, a dice roll, can be anything. Any action with a particular recorded outcome. Now let's go to the next one. So basically, an experiment is either deterministic or probabilistic. We'll see why that is. Let's go to the concept of trial. A trial is basically one execution of experiment, right? So you did this action once, that is one trial. So if you do it, so suppose if I flip a coin, right? If I flip a coin once and I get a heads, let me do it this way. Flip coin once, or rather let's put it this way, trial 1, I got heads, outcome. I flip coin again, trial 2, I got tails. So a trial is one execution of this experiment. So it can be again, and one execution of the experiment means if my experiment is experiment. So if my experiment here, if I define my experiment as toss a coin and then throw a die, and then okay, let's stick to 2 because if I take more the outcome space will become too large. So if I say this is my experiment, then trial 1 of my experiment will be I toss a coin, I got heads, and I throw a dice, I got number 2, right? This is my outcome. If I toss it again, rather if I perform my experiment again, I got tails and I got some number 6 as the outcome. So again, if I add another value, like say select a card from 52 cards, right? Then my first trial will have another option which is king, or let's say an ace. I got an ace in my second trial. So all 3 actions must be performed once for that to be a single trial, if that is how I defined my experiment, right? Now there are again two types of experiments. One is deterministic, and the other is probabilistic. So basically, deterministic means, as the name suggests, we know the outcome is defined. We already know. So like if I perform an action, then I already know what result it will give, right? So something like if I switch on a bulb, I know that light will be on. If I turn it off, I know it will be off, right? On, off. This is pretty straightforward. We already know the outcome of this experiment, which is turning on or off a bulb. Or if I have to take another example, like a math equation, right? So suppose I have something like 5x square plus, or maybe let's take a small number, 2x square plus 3x plus 2 equal to 0. Suppose I have this, or 2x square plus 3y plus 2 equal to 0, and my x value is 1 and y value is 2, suppose. Then if I insert these values, the result will always be the same for these values, right? So if I say something like 2x square, x is 1, so 2 plus 3 2 is 6 plus 2, which is 8 plus 2, 10. This will always be true, right? There is no ambiguity here, there is no unpredictability, or it's not random. If I perform an action, I know what my outcome will be. But probabilistic, that's not the case, right? When we say probabilistic experiment, it is like basically a lot of things you see in the real world are probabilistic. Not a lot of them, yeah, you can say a lot of them. 1 second. I don't know why the formatting is messed up. Oh no, I think it's correct. Okay. No, that's correct. Yeah, so I got distracted. Yeah, so probabilistic experiments. Basically, if we play a game of cricket or a basketball or any game, or a soccer, anything, you cannot really predict you cannot determine the outcome. Like if suppose team A and team B played, you cannot say that team A will always win or team B will always win, or maybe this team will always lose, something like that, right? There are a lot of elements involved, lot of variables involved, and so what we can do is predict the chances of A winning, or predict the chances of B winning, or A losing or B losing, but we cannot concretely say that A will only win. Every time you play this way, A will only win, or something like that. Same again, the probabilistic experiment, like again coin toss, right? You cannot always say that I will always get heads, right? Even dice roll is also a probabilistic experiment. You cannot say I will always get 6 or I will always get 3 or something like that. Same with a well shuffled card deck, right? That's also a probabilistic experiment. The outcome is unpredictable. It's random. So that's what a probabilistic experiment is. So yeah, I think that's it. I don't think there's anything else to explain here. So the next topic, let's talk about outcome. What exactly is outcome? So outcome is the result, right? When you perform the experiment once, you do the result of one single trial of experiment, right? The result of one single trial of experiment. It's not the result of the action, it's the result of the experiment, because an experiment can contain one or more actions, right? So the experiment can contain either a dice roll, or it can contain a coin flip, or it can contain both. So it's not the result of the action, it's the result of the experiment, of one single trial of an experiment. So suppose, let's take a single coin flip. So my current experiment is coin flip. So what are the possible outcomes of a coin flip? I can have a head or a tail, right? Nothing more, right? Can I get more? Let's say a hypothetical scenario where I flip a coin and it got stuck in a wedge, somewhere in between, like it didn't land either heads or tails. Is that possible? In a fair experiment, it should not be possible. The environment you set up, right? Your environment should be such that all the possible outcomes must be defined. So if your environment is an environment where it has some wedges and you see that the coin is like stuck in between, it's neither heads or tails, then that should also be part of your outcomes. So it should be something like I'll get heads, tails and stuck, right? If suppose your environment is such that maybe you are in some fantasy land and you flipped a coin and the coin basically vanished, then that should also be a part of your the outcomes. So as you can see, this set of outcomes must be very clearly defined for it to be a proper experiment. Let's see what. Let's look at the other example. Let's say a dice roll. So my current experiment is a dice roll, single action. So I'll throw a dice. I can get either 1, 2, 3, 4, 5, 6, given it's a 6-sided fair dice roll. So the experiment is basically dice fair dice 6-sided dice roll. So it has only 6 sides. Then the outcomes are these 1 to 6. If I have if my experiment is standard 52 card poker deck, suppose, then here how many we have? We have blacks 26, right? And reds 26, if I'm not wrong, 26, 2s 52, yeah. And each of these will have 4 suits, right? If I'm not wrong, it's 4 suits. One of hearts, one of diamonds, one of clubs, if I'm not wrong. I think it will look something like this, and one of what is it? Hearts, spades. It will look something like this. So each wait. You will have 13. Yeah, that's correct. No, wait. Okay, I don't want to speculate here. I'm not pro. Let's see. Yeah, so as you can see, there are 52 cards, right? And we have 13 of, there are 4 suits, 13 each, which is basically, yeah, that's correct. So each 13 of each, and basically you have cards from 1 to 10, and you have face cards, which is face cards. You have Jack, Queen, and King, right? And then the number 1 is the Ace. These are the standard cards. So what were we discussing? Right. So if I select a card from this, suppose if I select select a card, right? So that will be any one of these 52 cards. If I say select a black card, then I will get one of this 26 cards, right? The outcome will be one of these 26 cards. So all these 52. So okay, I was talking about outcomes. So the outcomes are all these 52 cards, right? Then yeah, let's now, so okay, there's one more. We talked about a single action experiment. So suppose if I have my experiment, if I define my experiment as all are fair, fair coin toss, two-sided, and which is plus fair six-sided dice roll. This is my, these two actions are my experiment. So then the outcome will be, I flip a coin once, I'll get a head. Then I throw a dice, I'll get a 1, right? It will be like, the outcomes will be like, I'll flip a coin again, I got a head. I throw a dice, I got a 2. Then I got a head, I got a 3, 4, 5, 6. Then I flip a coin again, I got a tail, I got a 1. I got a tail, I got a 2. I got a tail, I got a 3. Tail 4, tail 5, and tail 6. I have totally 12 outcomes. Here 52 outcomes for the card, and for the dice roll we'll have 6 outcomes. For a single coin toss we'll have 2 outcomes, right? For a coin toss and a dice roll we'll have 12 outcomes. So that's what outcomes are. The results will be something like this. The results will be this is a single outcome, because the experiment is both actions, right? Both coin toss and the dice roll. Let's go to the next one. So we are talking about fair coins, right? Excuse me. So fair or unbiased coin. So basically, a fair coin means the a fair two-sided. Let's say a fair two-sided coin means the chances of getting a heads and tails should be both 50%. The likelihood should be 50%. So if I toss a coin, if I toss it 10 times, 10 trials, I should see something like 5 heads and 5 tails approx. In small sample sizes you won't get, so we can increase it to maybe 10,000 times. So if I toss a coin 10,000 times, I should see approx 5k heads and 5k tails approx, right? So that's what it means. There should be equal likelihood for both the sides to appear. Same with the dice roll. So if I take, which is basically half and half, 50%, 50% for the heads and tails. If I take a dice roll, again, fair dice roll, 6-sided, right? Every side should have equal chance of showing up, given we take large number of trials. So something like each side should have a 1/6 chance of showing up, right? So if we add all these, then 6 by 6, that will be probability 1. We'll see why probability 1. That's part of the axioms of probability. We'll see why it's 1. But for now, you just have to know that each side should have a fair chance of showing up as you throw it a lot of times. If the sample size is small, then you will not see that that fairness appearing. But if you throw it large number of times, you will see that each side has an equal chance of showing up. Like equal in the sense like 1/6 approx. These are all approximate. Again, just to give you some trivia, I've read that US pennies have a slight bias on the heads side, right? So if you toss a US penny, it seems that it will fall on the heads more than tails. And also, you will see a lot of bias in the coin toss if the coin is not flipped properly. So you need to have lots of rotations. So if you don't flip it strongly enough, then the face that you are the face up, if you have faced it to heads or tails, that will be more likely to show up when you don't flip it hard enough. And the other reason, or rather, the coin toss can also get biased if the floor is sticky, or if it dropped on a mat. If you use the face as heads, and if it drops on a mat, there are more chances that it will fall. It will be a heads more than tails. So to avoid all these biases, the correct way to flip a coin, it seems, is to flip it hard, in the sense it should have more rotations and it should fall on a flat hard surface, so that even if by chance the rotations are low, when it hits on the hard surface, it will then bounce back, it will flip harder, and the bias is negated there, it seems. What else? I guess yeah, I guess that's about fairness basically. Now let's look at sample space. Sample space in set theory language, it's also called universal set. Basically, sample space is the set of all possible outcomes, right? It's set of all possible outcomes. For example, okay, what do I have to check? Yeah, basically the definition is it's the set of all possible outcomes of an experiment performed in a single trial. Example, if we take the example of a dice roll, we already saw this set of all outcomes of a single dice roll, six-sided fair dice roll, right? This is our experiment. This is my experiment, right? Trial 1, in a single trial, all my outcomes are basically these. So what it means is, if I throw a dice once, I can get either a 1 or a 2 or a 3 or a 4 or a 5 or a 6. Any one of these 6 values I will get. Similarly, if I choose if we do a coin toss, we already saw this, right? Now the experiment is coin toss, fair two-sided coin toss, then the outcomes, or rather the sample space S, will be either a heads or a tails, right? Same with the 52 card deck, standard 52 card deck, right? My sample space will be those 52 cards we saw, right? 26 blacks and 26 reds. Total 4 suits, right? Each having 13 cards each, which is basically this total set, right? You can have hearts and diamonds red, clubs and spades as black. Okay, where is this? What were we talking? Yes. Yeah. So that's the sample space. And by the way, sample space does not include or rather, sample space only includes possible outcomes that can actually happen. So suppose so like we discussed in the beginning, if my experiment basically coin toss, right? Again, when I say coin toss, I'm ignoring the fair. Assume always it's fair unless I explicitly mention it. It's a fair coin, two-sided coin. When I say coin toss, suppose it got stuck in between, right? That is not part of the fair two-sided coin toss unless that's the experiment you've already defined. If your experiment is such that you will have an outcome called stuck, it should be there. It should be there in your outcome sample space. Sample space is nothing but your set of outcomes, right, of performing that experiment in a single trial. Now we also saw if my experiment is coin toss and die roll, we already saw the set of outcomes here, right? Where is that? These. If my experiment is coin toss and dice roll, which is six-sided, this is my sample space. So here S is 12 outcomes. Single versus, okay, now the next is single versus multi-trial sample space. We already saw that, single versus multi-trial. Now, this is the multi-trial. Okay. Okay, multi-trial, fine. I guess this is the other one. When we say, now all here, every time we saw the outcomes for a single trial, one trial, one execution of this experiment. Suppose, and sample space does not limit to a single trial of an experiment. You can have multiple trials, and that can also have a sample space. So suppose I do my experiment, suppose, yeah, I guess I'll have to, experiment is coin toss, two-sided fair. Okay, this is my experiment. A single trial. Okay, trial 1, we do trial 1. Trial 1, what are my outcomes? My sample space will be heads or tails, right? Trial 2, my sample space will be heads or tails again. Now, if we define sample space for, wait, what is the question? Okay, single versus multi-trial sample. Okay, so if I consider sample space for for both the trials, then S for 2 trials. My S for 2 trials would be, I will get we will take the combination of both the trials. So I toss my coin once, I got a head. I toss my coin once, I got a head again. Let's say I toss my coin once, I got a head, and I toss it again, I got a tails. I toss it once, I got a tail, and then I got a head for the second trial, and then I got a tail on the first trial and the tail on the second trial. So this will be my sample space for 2 trials, right? It's a pair of combination of the outcomes of both the trials. That is how you define sample space for 2 trials of an experiment. Let's see. Now we got here 4 outcomes, right, for 2 trials. How do we calculate the total outcomes? So the total outcomes is we can calculate by the formula, which is basically the outcomes in the sample space to the power of the number of trials. So for a dice roll, sample space is what? Heads and tails, right? Which is 2. So 2 power the number of trials. So if we are doing in a single trial, the sample space is 2. But if we are doing it for 2 trials, then the sample space is 4. We saw it here. If it is 3 trials, it will be 2 power 3, which is 6. Wait, 2 is 4, it's 8, sorry. It's 8. So then the outcomes will be, I throw my first coin, I got a head, then I got a head, tail, head, I think head, tail, head. Wait. So yeah, head, tail, head, tail, head. One second. H. Okay, let's call it HTT, right? Then we have tail, then tail, head, then tail, head. We are missing something. 1 second. Head, tail. Head, tail, tail. what else, head, tail, tail, and head, tail, tail. Okay, I guess we missed tail, head, rather tail, head. Wait, so we missed, wait, let's plot it here, rather write it down. We have H, 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 T, H, H, T, H, and then H, T, T. Then we have T, 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 right? Tails, tails, tails. These are 4. Then we have tails, tails, head, tails, head, tails, T, T, H, T, H, T, and we have tails, heads, heads, right? So 4 here, 4 here, total 8. Oh, sorry, I guess I was blocking this. Anyway, we got the values here. So let's just verify. I don't think we have any tails, HHT. Yeah, so that's how you get yeah, so that's how you calculate the total outcomes, right, of the sample space across multiple trials. Now, this is, yeah, okay, I already showed you. This is the multi-trial coin toss example. Now we can do one for multi-trial dice roll. This will be quite huge. We'll see. This is basically multi-trial coin toss. This is for 3 trials. Now if we do a die roll for, we'll do for yeah, we'll do for 2 trials. This will become huge because what is the formula for a single trial? One trial, the sample space, or rather, yeah, the sample space is 6, right? For 2 trials, it will be just basically 6 power 1. The sample space will be 6 power 2, which is 36. So we'll see. So basically how it will be is, so we have our first set of 3, 4, 5, 6. Then we have second die roll. Again we get one of these, right? So the sample space will be something like 1, 1, 1, 2, 1, 3, so on, 1, 6. Same, next will be 2, 1, 2, 2, 2, 3, 2, 6. Then 3, 1, 3, 2, 3, 3, so on, 3, 6, right? Same, 4, 1, 4, 2, 4, 6, 5, 1, 5, 2, so on, 5, 6. And then you have, wait, so 6 plus 6 plus 6 plus 6 plus 6, 6 to 12, 6, 12, 18, 24, 30, and then 6, 1, 6, 2, so on, 6, 6, plus 6. So total 36 values, 36 outcomes. So when you do when you roll the die twice, the sample space will look something like this. Okay, sorry, I was covering it. So total 36 outcomes, right? This will be our sample space when you roll a die twice in two. So these are two trials, and the experiment is a single, or rather, experiment is rolling a die, only a single die. That's the action. That's the experiment. The outcome for a single outcome space for a single die is just 1 to 6. 1 to 6. The outcome space for two trials for a single die performing the experiment twice would be this sample space. I hope that was clear. Next, let's go to the event. So event is, the definition is basically, it's a subset of S sample space. It's a subset of sample space. It is basically a statement about the outcomes that are present in the sample space. So you can say, informally speaking, okay, I guess let me not say that, that might add unnecessary confusion. Okay, so yeah, basically the definition is it's a subset of the sample space. That's the definition. And the most the thing is, it's a subset of sample space that may or may not happen in the in a single trial of the experiment. So if you perform one trial, this sample space, the subset can or need not appear, right? It is something like, let's see, for example, if I have a, if I roll a dice, let's say my experiment is 6-sided die fair die, let's say. Right, it's a 6-sided fair die, and I'm doing first trial. My sample space is for a 6-sided fair die, it's 1, 2, 3, 4, 5, 6. Right now, the event is a subset of the sample space, which means my event can be something like let's not use E. E is actually event space. So let's say I have an event A. Event A, some random event where the chances of rolling a 6. This is my event. This is my event. I have a 6 as the outcome, right? So what are the chances of rolling a 6? My event is 6. Okay, so chances goes into probability. Let's say rolling a 6. The event is roll a 6, basically. Rolling a 6 is one event. And the other event is, we can have events like roll an odd number. Event B, roll odd number. So you see here, what are the odd numbers? 1 is odd, 3 is odd, and 5 is odd. So my event space, or rather, let me not say event space, my event. So my event B will be something like 1, 3, 5. Basically a subset of the sample space. It means these are possible not okay, let me not say that. When you perform the experiment, you are asking what are the chances of getting a odd number. Not chances, I guess that's not the correct way of putting it. What are the outcomes that will give me an odd number? So you will get an odd number if you have 1, 3 and 5, right, in the event. So again, this is slightly hard to explain, but I guess that's the only way to say it. Again, if I have an event, if I want an event C, which is roll an even number. So even numbers, what are my even numbers? I have 2, 4 and 6, right? So I will get an even number if the experiment performed gives a 2 or a 4 or a 6 right? So that's what that's basically what an event is. These are you have many types of events. I can have an event D where number is greater than 3. An event where the number is greater than 3. So suppose if I roll a die, what are the when will I get a 3? When will I get a number greater than 3? So the event, I will get a number 3 if I have 4, 5 and 6 in the event, right? So we'll do an example, I guess that will make it more clear. We'll see another event. So here my experiment will be, so events can be again events are statements about the experiment, right? So you can have single action events or multiple action events. You can have single trial events or multiple trial events as well. So we look at multiple actions here. Basically my experiment is I have a coin toss, two-sided, fair, and my action 2, action 1, action 2 is basically a die roll, 6-sided, fair. Okay. Let's see, what are we talking about? Events. So so event can be something like we'll take these two examples only. What are the possible outcomes when a dice is rolled and an even number has occurred, right? So the die is rolled, so and even so in this case just consider it as my experiment is performed, right? Experiment performed, one trial, and I got an even number. The coin toss is already happening. Don't think that just because the event defines just about the die, it doesn't mean the coin toss didn't happen. The coin toss is happening, but we are simply focusing on the event of the die roll. So we already saw the outcomes, right? So if the experiment is performed once, what will be the outcome? Possible outcomes will be I'll get a head or a 1, right? I'll get a head 2, head 3, so on, head 6. I'll get a tail 1, tail 2, so on, tail 6. These are possible outcomes. So if I perform one single trial of the experiment, then I can get either a head 1, head 2, head 3, or a tail 1, tail 2, tail 3, so on. Any one of these outcomes from this sample space. So what is the question? So the event. So the event where I get an even number. What all events here give me even number? I'll get my event A where even number will be, the events will be head 2 is even, head 4 is even, head 6 is even, right? And tail 2 is even, tail 4 is even, and tail 6 is even. So this is my event space, or rather the event where I get a even number when I perform this experiment, right? Similarly, another event can look like what are the possible outcomes when the dice is rolled and the number greater than 2 has occurred. So B is, this is our sample space for this experiment, right? So outcomes where number is greater than 2. So that will be head and 3, head and 4, head and 5, head and 6, right? And then we obviously have tail and 3, tail and 4, T5, T6. This will be my sample space for this event. This will be my event, not sample space, sorry. This will be my event for this, you can say, this statement will have this outcomes. These are the outcomes for this event, right? And if we look at the coin toss example, suppose what is the, let's say, one trial of experiment, what is the what is the outcome when or what are the outcomes when the coin toss, or rather what are the outcomes for heads, let's just say, for heads, we'll just take heads. So for this experiment, what are the outcomes for heads? We'll get all this. This will be our event space, this will be our event. These are all the possible outcomes in this sample space for this question, for this event, right? Yeah, I guess the more I explain, it might get unnecessarily confusing, but I hope that was clear. This is that's what an event is. It's a statement about the outcomes. Let's see. Let's look at multi-trial event. So events can also be considered in multiple trials. So let's take the simplest example, which is here my experiment is a fair two-sided coin. Okay, and this is trial 1. My sample space is head and tail, right? Now, what possible events I can have? Did we see the events? Oh, okay, we didn't see the event space okay, that formula will come next. Okay, let's see what possible events can we have here. We can have obviously a head as our event, we can have tail as our event, right? There is also something called empty set, or basically the impossible event, and then the sample space, or rather the certain event as our event space. I guess this is better if I explain it here. What is multi-trial coin toss example? Did we already look at this? Wait. Oh, so okay. This is multi-trial event, right? So fine. I guess yeah. Just ignore this for now. So basically, in single trial, these are the outcomes. This is our sample space. In multiple trials, let's see. I don't think it's good to explain it here. Sum is even. Okay, I guess we already saw multi-trial coin toss, right? So the sample space will look something like head tail, tail head, and tail for two trials. For two trials. What is this asking? Multi-trial coin toss. This is multi-trial coin toss. This is the sample space, but event space will be, yeah, I guess we'll look at event space here. I don't think this is the correct place for us to look at this one. Okay, let's ignore that. Now let's look at the dice roll. Yeah, so dice roll, the sample space we already saw here, right? For multiple trials. This is our sample space for multi-trial, basically two trial dice roll, right? So we can pick events from here. Let me try to copy this. Let's see. Okay, great. So we have our thing here. So yeah, let's see. I guess I'll shrink this a little bit. No, this is fine. Anyway, so multi-trial events will look something like this. So suppose the ask is sum is even. This is the event, right? If we look at sum is even, we will get some even event will look something like, let's call it A. We'll have outcomes. The outcomes of sum is even will be 1 plus 1, right? So 1, 1, then 2, will have 1 and 3, 1 and 1, 4, 1 and 5. Then we'll have 2 and 2, 2 and 3, 2 and 4, right? So on. The sum of these should be even, right? So 5 plus 1 is even, 6 plus 2 is even, 6 plus 6 is even. So you will have all these outcomes in this event. The next one will be first roll is 4. So if the outcomes for first roll is 4, we'll have all this 4 events, right? The one starting with 4. This set. These all will be our events, and both rolls equal. For this, the events will be both rolls equal. All of the diagonal elements, right? 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, 6, 6. So all these outcomes will be part of this event. So that is a brief about events. Let's look at the event space. I think that will be much clearer. Then the events concept will be slightly clearer. Event space, also called as power set in set theory. So the definition is, it's a subset. It's a set of all subsets of the sample space. Set of all subsets of sample space. Basically, all these events we saw here, right? In the experiment, it is the set of all these events, all possible events, that is called the event space or the power set. It is defined as E, set of all subsets of S. So excuse me. So yeah. So how do we calculate the total number of events? How do we know how many events exist for a single experiment? It could be right for a single trail. Obviously, this calculates for single trail. So we are calculating total number of events for a single trail. So total events will be, the formula is 2 power the number of elements in the sample space, which is the total outcomes. 2 power outcomes in S. It's to give you an example of the coin toss. Say, suppose my experiment is coin toss, two-sided. My sample space is what? Heads and tails, right? So the total events for this experiment for a single trial will be 2 power which is 2 power, our total elements is 2, which is 4. The 4 elements, the 4 events for this will be basically our, I will explain what these are. Empty set, which is 5, the certain event, which is our universal set, which is basically head and tail, and you have heads and tails. Okay, 5 is just standalone, so S is also standalone. Okay, so to write it, our event space will be 5 S head and tail. These are the 4 possible events you can have. So empty set is basically an impossible event. It is basically the complement of the sample space. So something like, it is like you are subtracting, okay, let me not say this now. Yeah, just think of phi as the impossible event. So it's like you toss a coin and nothing happened. Although it's impossible. There is no such thing as nothing happened, because if you toss a coin and nothing happened, the only way to put it is you did not perform the experiment. Okay, so phi is the empty set, which is basically the chances you perform an experiment and nothing happened. It's an impossible event. Impossible meaning probability is 0. This will never happen. But the probability theory actually requires, or rather forces this this event. Just give me a moment. Yeah. So it forces this event. Let's see. So that's what phi is, and then I will explain in detail how this shows up. Then you have S, which is our certain event, which is nothing but our sample space. Certain event. It's called certain event because it the entire sample space, which is our heads and tails, in this case, is also an event. It's part of the probability rules. So same, even the empty set is also a result of the probability rule, one of the axioms of probability. And obviously heads and tails are obvious events, right? Let's see. So these are the 4 possible events of a single trial fair two-sided coin. Let us look at all the possible events, or rather the event space of a 6-sided die roll. So the experiment is basically 6-sided fair die roll. So the trial is one. We are doing a single trial, and the sample spaces, obviously we know sample space here, 1 2 3 4 5 6, right, for a 6-sided die roll. Now let's see. So since we have 6-sided 6 sides, the event space, total number of events, total events will be 2 power 6, which is what is 2 power 6? I think 64, is it? 64. We have 64 events. That's a lot of them. We'll see. I don't know if we can. So 64 events, right? We'll see. So how do we know what these events are? Like we can look at something like the types of events, which is basically you will have simple events, which is okay. Before that, you will have your empty set, which is our phi, right? which is the impossible event. You will have one impossible event. You will have one certain event, which is our complete set. 1, 2, 3, 4, 5, 6. Let me shrink this, I think. Oh shit. Okay, yeah, that's fine. That's fine. We don't have to see that anyway. We have one impossible event. We have our certain event, right? Which is basically, this is 1, this is 6 plus 6. So we have 7 events here. Then we'll look at our simple events, which is basically single digit events. We can have, no, this is not 6, this is 1, sorry, this is 1. So we have 2 events here. This entire thing is one event, right? So I forgot, these are 2 events. We have our simple events, which is basically we'll have 1, 2, 3, this is one event, 4 is one event, 5 is one event, and 6 is one event. So we have 6 events here. And then we have our compound events. More than, so greater than one, so greater than one outcome. This is a single outcome. Single outcome, this is greater than one outcomes. So compound events, so we can have a set of two outcomes, right? 2 outcome values. We can have 3 outcome values, 4 outcome values, 5 outcomes, 5 values, and there is only one 6 value, which is our certain event over here, this one. So if we take 2 outcomes, like instead of writing all this, we can calculate this using the combinations formula, right? Permutations and combinations, the combinations formula, which is our this NCR n factorial by r factorial n minus r factorial. We will see what this is. For now, we'll just blindly insert the values. So n is 6 here. So 6c2. So what is 6c2? 6 by 2 factorial, 6 minus 2, 4 factorial. So 6 into 5 into 4 factorial will cancel the 4. So basically 3 into 2, so 2 gets cancelled, 5 3 is 15. So we will have 15 outcomes here for the two outcome, 15 events. We will have 15 events here for 2 outcome values. Then let's see, so let's say 6 factorial by, now 3 outcomes will, so 3 factorial, 6 minus 3, 3 factorial. So 6 into 5 into 4, 3 gets cancelled by 3 into 2, 2 2s, 3 2s, 5 2s are 10, 10 2s 20. So we will have 20 events in the 3 outcome, 20 events of 3 outcomes. Then we will calculate by r is what, r is 4. We will calculate 4 outcomes, 4 factorial, 6 minus 4, 2 factorial, 6 into 5 by 2, 3, 15. So again 4 outcomes will have 15 events. Then 5 outcomes will be 6 factorial by into 6 minus 5, that is 1. We will have 6 events of 5 outcomes, right? So if we total this, 15 2 is 30 plus 20 50. Here we have 56. 56 plus 6 plus 2 plus 6 plus 2, which is basically 62, 64. So that is how we will have 64 events. It kind of matches our formula value, right? And this 64, obviously, we can define all this, but that looks tedious anyway. Yeah, we'll just try to do that. So 15 events, 2 outcomes. So 2 outcome values will have 15 events. Something like 1 2, 1 3, 1 4, 1 5, 1 6, 2 1, 2 2, 2 3, 2 4, 2 5, 2 6. No, 1 second. Okay. So the set. 1 second. It's not these. The outcomes will be. 1 2 1 3 1 4 1 5 1 6. 2 1 and 1 2 are same, so we don't take that. Then 2 2, 2 3, 2 4, 2 5, 2 6, 3 3, 3 4, 3 5, 3 6, 4 4 4, 4 5, 4 6, then 5 5 and 5 6, and that's it. So you have 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15 16 17 18 19. 1 second, I think something's wrong here. Yeah, I mean 2 2 are same, right? So this is these are not present. So now you see 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15. So these are 2 outcome events. Yeah, that was a mistake. So let's look at 3 outcomes. So for 3 outcomes, you have 20 events. So we can say 1 2 3, 1 2 4, 1 2 5, 1 2 6. I'll remove the commas because that's but assume there are commas. So you have that's for ones. Then 1 so 1 3 1 3 4, 1 3 5, 1 3 6, then 2 2 3 4, 2, 3, 5 and 2, 3, 6. 3, 4, 5, 3, 4, 6, 4, 5, 6. 4, 5, 6, wait, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. What did we miss? So 1, 2, 3, 1, 2, 4, 1, 2, 5, 1, 2, 6. One, the 1, 3, 4, 1, 3, 5, 1, 3, 6, 2, 3, 4, 2, 3, 5, 2, 3, 6, 3, 4, 5, 3, 4, 6. Wait, 1, 3, 4, 1, 3, 5, 1, 3, 6, then 2, 3, 4, 2, 3, 5, 2, 3, 6. Okay, we do have 2, 4, right? 2, 4, 5, 2, 4, 6. That is also one thing. Then we have 2, 5, 6. That is the other one. Then we go to 3, 4, 5, 3, 4, 6. Then we also have 3, 5, 6. Then we go to 4, 4, 5, 6. Okay, let 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. 3 more are missing. What else? 2, 3, 4, 5, 3, 4, 6. Then 3, 5, 6. We went to 4. Okay, we missed 5, right? No, but 5, 6 becomes 2 outcomes. 1, 2. What else are we missing here? 1, 2, 3, 1, 2, 4, 1, 2, 5, 1, 2, 6. Then 1, 3, 1, 3. Okay, wait, we missed 1, 3. Not 1. So we also need 1, 3. 1, 3. No, that is there. 1, 3, 4, 1, 3, 5, 1, 3, 6. Yeah, something like this. I don't think. Yeah, I'm not sure what I missed here, but something like this. You'll get 20 outcomes here. For 4 outcomes, will look something like this. I'll just show you the overview. So 4 outcomes will be 1, 2, 3, 4, then 1, 2, 3, 5, 1, 2, 3, 6. Then you'll have 1. So 1, 2. 1, 2, 3, 4, 5, 6. 1, 2. 1, 2. How many are 4 outcomes? 15 events. Oh my god. What will we get? We can get something like 1, 2, 3, 4, 1, 2, 3, 5, 1, 2, 3, 6. Obviously, we'll have a 2 series, then 2, 3, 4, 5, 2, 3, 4, 6. So on. You'll have some other numbers here. yeah, you'll have a 3 series. No, probably not 3 series. Something like this. And then you will have a 5 outcome series, right? So you'll have 1, 2, 3, 4, 5. Then you'll have 1, 2, 3, 4, 6, and so on. So that's how you will see the total number of outcomes, and that will add up to 64 for a single trial of a dice roll. You will have 64 subsets of the sample space, basically 64 events, total events of a single dice roll, of a single trial of this dice roll experiment. Now let's look at yeah, I guess this is unnecessary coin toss. We already did this. Now let's calculate. Now let's look at the probability formula. How do we calculate probability? Excuse me. So the probability formula is P of a particular event would be the possible outcomes by total number of outcomes, which is nothing but our sample space. So possible outcomes by sample space. So if we take an example, suppose okay, so yeah, let's take an example, which is our the experiment is coin toss, right? What is the possibility of getting a head? A head, right? Head is one outcome, right? So which is 1 by sample space is what? Head and tail, right? Which is 2. So possibility of getting a head is half. Same with tail as well. Right, now let's take another experiment, which is our dice roll. So let's say, what is the possibility of getting a single number? A single number would be 1 out of sample space is what? 1, 2, 6, right? So total 6 numbers, 6 outcomes. So 1 by 6 of getting a single number. Suppose we take, let's take this example. What is the possibility of getting an odd number? Suppose odd number, right? What is the set of odd numbers? 1, 3 and 5, right? So the total outcomes in this event are 3. So possible outcomes, possible outcomes of this event are 3. Total outcomes are 6. So that is 3 by 6, that's half. Same with even number. What is the possibility of getting an even number? What are our what is the event for even number, which is 2, 4, 6, right? Again, the total outcomes, possible outcomes in this event are 3. So 3 out of total outcomes, which is 6. Basically half. If I say, what is the possibility of getting a number greater than 2? What is the event space? What are the outcomes for this event? So greater than 2 is 3, 4, 5 and 6, right? Total 4 outcomes. Oh, sorry, I'm not showing. 4 outcomes. So then the probability of this event, let's call it event A, probability of this event will be possible outcomes are what? 4. Total outcomes, sample space, which is our 6, which is 2 by 3. That's how you calculate probability. Let's take just one more example, which is our card example. So let's say we have the set of 52 cards. This is our experiment is 52 card deck. Standard is basically the 52 cards, the standard poker deck. What is the probability of drawing a red card? So of these, we know, right, there are 26 reds and 26 blacks, which total to 52. So the probability of drawing a red card is, so the possible outcomes are 26, right? So if I draw, okay, so if I draw a card from this 52 deck, I have 26 chances of getting red. So my possible outcomes are 26. 26. Total number of outcomes are 52. So that's half. Right? Same with black. What are the chances of drawing a black card? Again, you will have 26 by 52, which is half. Suppose let's say the question is, what are the chances of drawing a face card from 52 cards? What are face cards? So we have face cards are these things: Jack, Queen, King in all the 4 suits. So how many face cards are there? We have 3 4s, 12, right? 12 face cards, right? So possible outcomes are 12. Total outcomes 52. So basically 12 by 52. What is this? 12 2 6. Three by 8, right? So that's the probability of drawing a face card. Suppose if you have a question, no, that's fine. I think that's enough. I think you have some idea now. You must be having some idea. That's basically what probability is. Now let's look at the notation of probability. So if I write something like P of A equal to the possible events. So I have to write something like possible events of A by total number of events. I have to use these pipes. This is called a cardinal. Basically, what this means is A is a set, right? A is an event. An event is a set, right? I might have maybe 2, 4, 6. This is a set of even numbers. This is my event. This is a set. So so when we are writing in probability the notation, we have to write something like the number of elements in this event by the number of elements in the sample space. The pipes represent the size of the size of the set. If we don't put these pipes when we are writing something like this, it means we are dividing the set by the sample space. That makes no sense. So this is incorrect way of writing. So the correct way of writing is you have to put these pipes or the bars which represents you are taking you are dividing by the length of this event. You are dividing the length of this event by the length of or rather the number of elements of the sample space. That's basically the set notation. Generally we might think this is modulus, like modulus of a number, like say 3 would be the absolute value, which is a 3, right? In probability we use these pipes for sets, not for numbers, so that must not be, you should not get confused with that. We use this pipes for a set to indicate that we are taking the number of elements in the list and not the list itself, or number of elements of the set, not the set itself. We don't divide the set by another set. We simply divide by the numeric values, which is the cardinal, which is the number of elements of the set, by the total number of elements of the sample space. Elements of the set event by the elements of the set of the sample space. So that is those are the rules, some minor stuff. Now let's go to set operations. Did I cover empty set? Okay, that's coming there. Okay. Set operations. Okay, I guess this size is necessary. So let's look at set operations. Set operations. So if you search this in Google, you will get something like this. Okay, not this one. Not this as well. Desmos set. Should be set operations. Why is it? Okay, if you don't get it, then you'll have to remember this link. So you will be directed to something like this. Maybe, wait, Desmos set calculator. Interesting. Okay, anyway, you'll have to remember this link. So basically, so set operations, basically you have 3 operations: intersection, union, and complement. These are just different, yeah, you could say different operations on sets. Let's see. How do I just show this? Okay, we'll take this only. I will first. Yeah. Okay. I'll go this way. So let's look at the events first, and then we'll get into the operation. So it says. So we have an event A. Event A says Mohit bets that he will get an odd number. So the experiment here is a die roll, 6-sided, fair of course, and number of trials is 1, right? Number of trials is 1. Our sample space is obviously 1, 2, 3, 4, 5 and 6 for a die roll. Now event A here is Mohit bets that he will get an odd number. So what are the outcomes for odd number? 1, 3 and 5. We already saw this. Event B, Rakesh bets that he will get either 1, 5 or 6. So he's betting on 1, 5 or 6 outcomes. What is event C? Abhishek bets that he will get an even number. So what's the even? 2, 4 and 6, right? Outcomes. Then event D, rolling a number greater than 3, strictly greater than 3. So 4, 5 and 6. So these are our 4 events. Now we can perform set operations on these events. So intersection means basically elements of A, elements of set of a particular set must also be present in the elements of the other set. To properly visualize that, I think intersection, this one. So elements of this and elements of this, the intersection of these two sets will be this area. So basically when we perform an intersection, we will only get the elements that are common in both the sets. Let's see, what's the question? Yeah, so basically that's the definition. The question is, in which condition both Mohit and Rakesh will win their bets? So you see here, Mohit is set A, Rakesh is set B. In which condition both Mohit and Rakesh will win their bets? So condition means in when, what is the event where both of these people will win, right? So if we get a 1, right? If both of if the event, when we roll a die and we get a 1, in that case both these people will win, right? So that's what intersection means. So it's basically A intersection B. This is the symbol for intersection. The event will be 1. The formula, again, you'll see the formula, I guess, in a different section, because that requires knowing types of events as well. Yeah, so that's what so that's what basically intersection means. We'll look at some Python code. Let's see. Or rather, let's look at the probability first, then we'll look at the Python code. So probability of both Mohit and Rakesh winning, which is basically P of A intersection B is A intersection B by S, right? This is the formula. So A intersection B is 1 by S is 6. So the probability of both of them winning is 1 by 6. If you look at the code, we can actually use standard Python code. I'll just do it in Jupyter Notebook. I think that will be quick. So let's take event A is, what's our event A? 135. 135. Event B is 156. We are taking sets, right? Sets in Python we use curly braces. So intersection is nothing but we know A and B. So both elements have to be in both these sets. So if we do A and B, we get 1 and 5. Oh, okay. Right. So we have 5 as well. I missed this. So Mohit and Rakesh will win if the outcomes are both 1 and 5. So if when we roll a die and if the outcome is either 1 or 5, in that case these both will win. So the probability will be 2 out of 6, which is 1/3. My bad. That was I think my writing was, I got confused with my writing. So you have 1 and 5 as well. Correct. So these both are common in both sets. So that's how you do intersection. Let's see. Saw the Python code. We saw the problem. Yep. Now let's go to the union. What is union? Union is also called as addition rule. I think in set theory it's called addition rule. Basically, union is, the definition is elements of A must be either in set 1 or set 2 or both. The elements must belong to both either set 1 or set 2 or both. So if we have two sets, the elements must belong to this or both, right? If you look at the visualization, union. So you see here, it's basically you will get the complete list at the end. It's you have both the elements must belong to either A or B or both. That's when it's called union. Let's look at the question. When either Mohit or Rakesh will win their bets. So who is okay? So Mohit and or Rakesh. So 135 and 156. 135, 156. So if we do a union B, what it means is we are adding both the sets. So we will have 1, 3, 5 and 6. So the result will look something like this when we do a union. So the question is when either Mohit or Rakesh will win the bet. So the emphasis is on or. When will either of them win their bets? So either of them will win their bets when we do a dice roll, and if the outcome is 1, 3 or 5 or 6, when either of these outcomes we see, then these both either of them will win. Then both of them will win. So the probability will look something like P of A union B is A union B by S, cardinality of A union B by the cardinality of S, basically the elements, number of elements of the set A union B by the number of elements of the sample space, which is basically 4 out of 6, same 2 out of 3, 2 by 3. So that's the probability of both of them winning. If we look at it in the code, for A union we will do simply or there is 1 3 5 6, right? That's exactly what we have here, 1 3 5 6. So yeah, so there is 2/3 chance of either of them winning. Now we will look at joint and disjoint events. I'll explain briefly here because we will go through that in types of events. So basically union is different for joint events and disjoint events. What's a joint event? Joint event is nothing but let's see, joint event is also called as non-mutually exclusive, which means events can happen together, to put it simply. So the formula for joint events is A union B will be P of A plus P of B minus P of A intersection B. Why are we doing A intersection B? Okay, I'm not sure if my writing is, yeah, it's not good. Let me. This is A intersection B. Let me just write it again. Joint events is so P of A union B is P of A plus P of B minus P of A intersection B, right? The reason why we are subtracting A intersection B is because if you see the events, if you see the let me just show it here, I guess that's better. So if you see the events, when you know that sets are unique, right? Sets must be unique. So when we are performing a union, we want to get rid of the duplicates, right? We don't want 2 5s and we don't want 2 1s in the result set. So to get rid of those duplicates, we subtract the intersection. So we do an intersection. What did we get? So from this 1 1 3 5 5 6, we are getting rid of the intersection which is 1 5 and 1 1 and 1 5, right? That is what this is. So this is the union minus A intersection B is this one. So that will give us this result basically. We want to get rid of the double count. So this is the formula for joint set. So what is P of A? P of A is 3 by 6, right? We have 3 elements. P of B is also 3 by 6. and P of A intersection B is what is it, 2 by 6, right? We have two elements here for A intersection B. So this is 1 by 2, 1 by 2, 1 by 3. So if we look at the probability, P of A plus P of B, that is 1 by 2 plus 1 by 2 minus 1 by 3, which is 4, which is basically 3 plus 3 minus 2, 3 to 6, so 6 minus 2 by 6, which is 4 by 6, 2 by 3, right? We see here that's the exact thing, exact same result we also got from the final set. So that's how you compute probability for joint events. If the events are disjoint, as the name suggests, disjoint means mutually exclusive. Mutually exclusive meaning two events cannot happen simultaneously. Suppose I'm rolling an even number, right? If the outcome is even, automatically it means that it's not odd, right? So when we are expecting an even, the odd cannot happen, right? If the event is even, you cannot have an odd event. So that's what if suppose in a coin toss you get a tail, or the event is a tail, you cannot have a head event, right? Only the and vice versa. If you have a head, you cannot have a tail. Such events are called mutually exclusive, or basically disjoint events. The occurrence of one event prohibits the occurrence of the other. So in such scenarios, the formula will slightly change. So we have P of A union B. The standard formula is P of A plus P of B minus P of A intersection B, right? So if we take the intersection for disjoint events, so what is the probability of an even and odd? It's 0, right? It will never happen. So the formula will only be P of A plus P of B minus 0. So this will only be the formula for disjoint events. So if we plug in the above scenario, then the probability will be probability will be 1. I don't think yeah, it is just remember the formula anyway. What is the question? Yeah, for joint events and for disjoint events, that's the formula. Anyway, we don't have to calculate the probability. That's the above scenario is a joint event, so that makes sense here. We got 2 by 3, right? So that is basically the union, or this is what is called the addition rule. Now let's look at the complement. So complement is the definition is it's what's the definition? You're basically the complement of an event is basically you subtract the event from the sample space. So it is all the elements of the sample space except the elements of that event. That's basically the definition. So it looks something like this: AC or A dash for A complement. Suppose an event's complement is S minus A. Basically, if I have to read it, so if I have to say it in a plain language, when will we not get heads? Or something like when will we not get even numbers when we roll a die? So what we can do is we can take the sample space and subtract the odd numbers, odd event, to get the no sorry. So the question was, when will we not get even numbers? When will we not get even numbers? When we get odd numbers, right? 1, 3 and 5. So what we can do is, if we subtract this even numbers, it's called this event A complement will be our odd numbers. This will be our odd event if we subtract it from the sample space. Let's look at the example, the question here. When will Mohit lose his bet? So what was Mohit's event? Let's take down all these things just to C is 2, 4, 6, 2, 4, 6 and D is 4, 5, 6. 4, 5, 6. A is basically is who? A is Mohit. B is Rakesh. Who is C? C is Abhishek. And D is just D. Let's keep D the way it is. So basically, the question is, where is yeah? Okay. So the question is, when will Mohit lose his bet? So he will lose his bet if the outcomes are 2, 4 and 6, right? So he bet on all the odd numbers. So if the event turns out even, then in that scenario Mohit will lose his bet. So this is like the perfect example for complement. So if we see here, all we have to do is, so one so bit, so the events when he loses bet is 2, 4, 6. So all we have to do is, our sample space is 1, 2, 3, 4, 5, 6, right? So if we subtract sample space and Mohit's outcomes are these, right? So if we subtract Mohit's events from the sample space, you will get our complement of A complement, which is the outcomes where he'll lose his bet. So this will be 2, 4 and 6. We'll look at it in the code. I think that will be clean. So A complement is nothing but S. So where we have to define our S. S is 1, 2, 3, 4, 5, 6. So now if we all we have to do is S minus A. There you go, 2, 4, 6. So that's the complement. These are the outcomes where Mohit will lose his bet. Yeah, that's it for complement. Let's go to the next topic, which is empty set. This is nothing but one of the events of in the event space, right? We already saw the event space here, the power set. There, let me just refresh the memory. I'll take a simple example. The experiment is two-sided coin toss. We are doing one trial, right? Number of trials. Our sample space is what? Head and tail. What is our event space? Event space E is basically head, tail, then phi, which is our empty set. That's what we'll discuss now, which is the impossible event, and our sample space, which is S, which is the certain event. So the empty set is basically the impossible event. Why it's impossible? Because when you perform an experiment, it is basically forward in time. You are either doing it or you are not doing it, right? So there's no question of So basically there's no question of when you perform an experiment and it returns an empty, it does not return an outcome. As we have seen in the first topic, the experiment is basically, if you perform it, it must give an outcome. It must fall in the set of outcomes. If you perform the experiment and it does not give any result, or rather, let's say you flip a coin and it disappeared, then it must be the outcome called disappear must be part of your outcomes, your sample space. So your sample space then looks like head, tail, disappear. This will be a third one. If it got burnt, then that must also be part of your sample space. So it must be burnt, right? Any possible outcome that happens must be in your sample space, in your list of outcomes. So, which is why the empty set, you perform the experiment and nothing happens, is invalid. It's not an actual outcome, but it is a valid event. It's a valid event as per the rules of probability, which we will see here. It's basically the Kolmogorov axioms. I will not go too deep into it. I'll just give a very brief overview of what it is. Just to understand what the empty set is. So, for example, what are the scenarios you will get an empty set? So, on a 6-sided die, if we are asking for a 7, that's an empty set, right? There's no 7. Or pick a black in a red deck. So if I have 26 red cards and I want to pick a black card, I will get an empty. That's when you will have an empty outcome. You will not have an outcome there as well. But it's not, the emptiness is not the outcome. That's what we have to remember. It's an event, but it's not an outcome. And it's an event only in the sense of a placeholder, just to satisfy the mathematical rules. It's just it's just a placeholder. It doesn't have any real meaning other than it being in the event space. The probability for an empty set is 0. It's called 0. It's considered 0, which means the experiment not necessarily. How do I put it? Yeah, just you just have to know this, that probability is considered 0 for discrete countable set of outcomes. Now that's where the there is a slightly tricky scenario. For discrete probability spaces, the empty set is 0. Probability is 0 for empty set. But for continuous probability spaces, okay, is the probability is still 0 for finding specific numbers, but it's not considered an impossible event. In basically all the experiments, there is only one impossible event, which is the empty set. This is standard, and for all impossible events, the probability is 0. Now the place where probability 0 is not considered as impossible is in the continuous probability spaces. Now, what are these discrete and continuous probability spaces? Let me briefly explain. Discrete probability spaces. So a discrete probability space is nothing but a countable set. Think of it as set of numbers, basically integers, right? So you can you know the next number of each number. So if I say 1, the next number is 2, the next number is 3, 4, so on up to infinity. So it's also called as countable infinity. There is only one infinity here. There is only one infinity, or rather you can say 2 if you assume negative infinity as well, right? There is a positive infinity and negative infinity. Basically it's a one single infinite list. You can think of it that way. And the reason it's countable, because we know what the next number is, right? Which is why if I say find what is the probability of an event where I get a 3, I know the probability, right? In the sense that I can count to this number in a list, in a set of say 6 numbers. So I will get 1 out of 6 for probability of 3. But and also in this scenario, you will have an impossible event where the probability is 0, because this is countable set of numbers. The coming to the continuous probability spaces. Here it's called continuous because this deals with real numbers, basically all fractions, decimals, everything. So this is uncountable infinity, uncountable or infinity, which is basically you between every number. So between 1 and 2, you have infinite number of numbers here, right? And between 1, let's say, and if I try to step in, if I say between 1.1 and 1.2, here also you have infinite number of numbers. So if I suppose say what is the next number of 1.1? Is it 1.11 or 1.111 or 1.1211? Like there is no limit here, right? It's between every two numbers. So even if I take what is the next number of 1.11 and 1.112, 1.112, I have infinite numbers here as well. I cannot say 1.111 is the next number or 1.1112 is the next number. So as you can see, we don't have a finite set of it is infinitely dense between each and every number. So in such scenarios, if I ask you to find the probability of, let's take a simple example, let's say 1.1 1.3, what is the probability of finding number 1.2? It's impossible. You cannot find in this probability space, because it's like again I told you, right, there are infinite numbers here. So finding 1.2 is pretty much impossible, almost impossible. But it's not considered an impossible event because 1.2 actually exists on the number line. So if we plot the number line, you will get 1.2 somewhere if you have the patience to, not the patience, it exists. Like it's not a question of patience. The number 1.2 exists, we know that, but we cannot the chance of hitting that number is incredibly, it's almost impossible. It's considered impossible in probability. So which is why p of a fixed number, let's say 1.2, is also considered 0. But this is not an impossible event. It's not impossible event. That is the difference here. So probabilities are calculated differently. So we take something like what is the probability between 1.2 and 1.3? The probability will be 1.3 minus 1.2. That's a whole different calculation, which is what is it? Is it 0.1? Yeah, it is. It's 0.1. So no. What is 1.3 minus 1.2? Yeah, it is 0.1. Okay, it is 0.1. So what was I saying? Yeah, so not all probabilities equal to 0 are considered impossible events. So that's the thing to note there, because it's only considered an impossible event in the discrete probability spaces where the numbers are countable. You know the next step of each number, the next number of each number. So now let's look at the fundamentals of probability, where the probability theory is built upon. That will give a good idea on why empty set is considered, this impossible event is considered in the as an actual event. So Kolmogorov axioms, basically foundations of probability. So what if we look at, so I'm sure many of you must be knowing the definition of axiom, but basically if you are not familiar, an axiom is just like the building blocks of anything, of a theory of anything. So you can say for a building, for like a brick and mortar building, the axioms are like the bricks, right? These are the building blocks. So these are the primitives, these are like the rules that define the game, the probability, the system the rules that govern the system. So all of probability theory is built based on these three axioms. There are two types. There are two views of these axioms. So one is the set theory. So the you can view them based on set theory view, or there is also a probability view. Probability is something. So it's set theory closure rules or something, this one, and the other one is probability measure view or something. These are two different types of views, but the axioms are the same. They are just two different interpretations. So what set theory says is, it is describing what events are considered how do I put it? How do you define an event? It is telling what is considered an event in probability. So it is saying the sample space is itself an event. So we saw in the if we see the if you see the event space of a coin toss, you see here this is the entire sample space, right? This is basically this, right? So entire sample space, which is the certain event. So the first rule is the entire sample space is an event. One second. Sample space is event. That's basically a rule. It's just something you have to remember. That's there's no proving these things within probability system. It is what constructs the probability theory. So these are just like stuff that you have to remember. The sample space is an event, and the complement of events are also events. And the third rule is countable unions of events are also events. So complements we saw, right? These are like what is the complement of a head? It's the tail. So in fact, this is the primary reason why the empty set exists. So what empty set says is the complement of the sample space. So complement of S complement is what? So you are subtracting sample space with sample space. So S complement is 0. So which is nothing but null set, right? So that is where this is fundamentally why the empty set exists, due to this second axiom. The third one says countable unions of events are also events. So countable meaning what we saw just now in the discrete spaces. It should be like integer based unions performed on integer based sets are also considered as events. This is the set theory view. So if we look at the probability measure view, we have the same things, just represented in terms of probability measures. So something like non-negativity. Non-negativity means probability values are always positive, right? 0 and 1. So it's positive in its flow of time. It either happens, which is 1, or it doesn't happen, 0, or things in between. There is no like a negative. There's no negative event, right? Like if I drop a glass and the glass is broken, you cannot unbreak the glass. I hope that was I don't know if I'm explaining it properly, but that's what it is. Non-negativity means so probability theory is it has three things, which is basically you have the sample space S, E is event space, and P is the probability function. So for an event A that belongs to E, what non-negativity says is P of A has to be greater than or equal to 0, meaning you cannot have it's always 0 or greater, the probability. Just think of it that way. I don't think explaining it more will only confuse excuse me, will only confuse you further. So just think of it this way, the probability is always 0 or positive. The second condition, what it says is normalization. Basically normalization means the sum of all the outcomes in the probability, the sum of all the probabilities of the outcomes in the sample space is 1. So let's say you have heads and tails for a coin toss, right? So the probability of heads is half, right? Because possible outcome is head and total outcomes is total number of elements in the sample space, which is 1 by 2 plus 1 by 2, which this equals to 1. So that's what this means. And the third axiom says additivity. This is our union thing. What it says is for disjoint sets. For disjoint sets, it says P of A union B. Obviously, disjoint means the intersection becomes 0, right? So P of A plus P of B minus P of A intersection B. This becomes 0. So the additivity rule is simply P of A plus P of B. This is the probability axiom. You don't have to remember all this. You just have to know that based on these axioms, what it's saying is, what the theory assumes or rather claims is, because the complement of the sample space must exist. Why the complement? So first, why complements exist? Because we want to know the things that are not happening as well, right? So there are events that are happening and events that are not happening. So we want to know both of them. So the not happening, how do we know? So if we know the complement of not happening, so not happening complement is nothing but sample space minus the happening events, right? Happening outcomes. So using this rule, what they say is there should be a complement for the sample space as well, because that's also an event as per the axioms. So the complement of sample spaces, what is the complement? We subtract an event from the sample space, right? So we are subtracting the sample space from sample space. So that is why you get 0, which is nothing but empty. So you get no elements in the set, which is why you have an empty set, or rather the impossible event. This is just a theoretical event. It does not happen in real world. It does not happen in the real world, right? Just to show you an example how that works. Okay, I think I forgot to show you that in here. So when we are calculating total events for the event space, right? Let's take the experiment, which is our coin toss. Two-sided coin toss. So when we are taking this experiment, which is of course fair, what is number of trials is 1, and our sample space we know, right? Heads and tails. So what is our event space? Our event space, as per the formula, 2 power the outcomes in the sample space. Outcomes in S, which is 2 power 2, which is 4. What are our events? We have our heads, we have the tails, we have our empty set, and we have our certain event. This I think certain event, the reason is probably clear. The event itself is heads and tails, right? And this is nothing but our sample space. So when we perform an experiment, it must, if we defined our experiment properly, the outcomes of the experiment properly, it must, the outcomes must be either a head or a tail. It must be present in our outcome list. So whatever outcome it gives, it must be present in our sample space, right? So that's why it's a certain event, because all the outcomes are present in this event. So whatever outcome it gives us, it is bound to happen. It's bound to occur. So that's why this is certain event. Now, why do we have 2 power? What is this? How did this formula come? So why is 2 power outcomes in sample space? What is this 2 here? So the 2 is nothing but included or excluded. So it's either present in our event or it's not present. It's either present or not present, right? So that's where the 2 comes from. So if suppose, if we take the coin toss example, our sample space is heads and tails, right? So the events will be, I have a head which is included or excluded, and I'll have a tail which is included or excluded. So if we combine the events, so if we combine the events, we will get head is included, right? Tail is included, which is nothing but our certain event, right? We have head is included and tail is excluded, which is our heads alone. Then we have then we'll go to tail is included, right? And head is excluded, which is our tail event. And then we have excluded, which is head is excluded and tail is excluded, which is our empty set. So that's how you get the event space. So that's why the formula is 2 power outcomes, number of outcomes. What were we discussing? Yeah, so yeah, I hope that was clear. That's why the empty events, that's how empty event, that is why empty event exists. Let's put it that way. Let's go to the let's go to the next topic, which is types of events. So we'll take the same sample events that we have taken here, right? Set operations. There are 4 types of events, which is basically mutually exclusive, non-mutually exclusive. We already saw this briefly before. So let's take the first one, which is mutually exclusive. So mutually exclusive means if one happens, the occurrence of one event will prohibit the occurrence of the other event. So basically, if I get an odd number, I will not get evens, and if I get an even, I won't get a odd. I won't get an odd. If I get a tail, I won't get a head, and if I get a head, if my event is a head, I won't have a tail event, right? So that's why it's called mutually exclusive or disjoint event. So suppose we take A intersection C, right here. Let's do it here. If I do A and C, you see here I'm getting a empty set because this is 135 and this is 246. So the first A is all odd and C is even. So we are trying to find the outcomes where these both occur at the same time. Right, A intersection C means the probability of both these events occurring at the same time or one after another in the same. You could say in the probability of both events occurring together. You can see here since odd and even don't occur together, we have an empty set, right? Similarly, so similarly, if we take non-mutually exclusive events, what is non-mutually exclusive? Non-mutually exclusive. So mutually exclusive is disjoint. Non-mutually exclusive is basically joint events. So joint events is nothing but you can have an overlap of, or rather to give the definition, two events can happen together. Let's to put it that way. So if we take A and C, suppose, so we have A is 135 and C is 246. If we do an A intersection C, can these two happen together? And no, sorry, not A and C. C and D. Let's do a C and D. So 246 and 456. So if we do an intersection of C and D, so you see there is 4 and 6. Right. So we have an overlap of elements. I think I'm. Forgetting the definition. Non-mutually exclusive. So mutually exclusive means occurrence of one does not occurrence of one affects the occurrence of other. So non-mutually exclusive. See. So the idea is both the events can happen together. So that's what it is. So as you can see, there is an overlap of outcomes, right? That is non-mutually exclusive. And if we look at independent events, so basically when we say independent events, the occurrence of one event does not affect the occurrence of other. So suppose we have two actions in the experiment, something like a die roll and a coin flip. So if I perform a die roll, does it affect the occurrence of coin flip? Not really, right? These are two separate actions. So one action does not affect the probability of occurring of the other action. So that is what independent means. There is a formula for independence. If two we so the strictly speaking, two events are considered independent. So let's take event A and B. Two events are considered independent if P of A intersection B follows this formula, P of A into P of B. So if this is like the test of independence. This is two events, the probability of two events happening together. So if you are given the probability of two events happening together, and if you want to check if both the events are independent, then this should tally their individual probabilities when multiplied should match the intersection of both the events. That is the formula related things. Let's see. These are all for dice roll, so this does not make any. It does not make any sense to do it here. Yeah, I guess that is it for independent events. There is nothing more to say. It's just two events are independent if the occurrence of one does not affect the occurrence of the other, right? I feel like I'm missing something, but yeah, I guess that is it for independent events. If there is, if I missed anything, I'll probably cover it in the next class anyway. Let's jump to exhaustive events. So exhaustive events is basically nothing but A union, B union, C. All it does is we combine. The combination of all these events will give us the original sample space. So in this example, so if we do a union B union C here, which is A or B or C, this will give us our original sample space. It is the set of all possible, it is the combination of all the outcomes of the events, which will give us nothing but our sample space. That is basically what it is. So that's about types of events. Let us look at the a small example where we'll analyze Sachin Tendulkar's ODI records for India. Let's see, do I still have? I have, okay. Okay, so I'll use this data set called Sachin ODI. So let's do our usual ceremony, which is pip install pandas, pip install numpy, do both and then import numpy and pandas. Okay. Now let's load our dataset. df is pd dot read csv. Our dataset is genodi dot csv. df dot head. So these are basically Sachin Tendulkar's ODI records. His performance, the number of sixes, his wins, and all that, number of centuries, all of that info. If we look at the data frame shape, there are about 360 records. Okay. Now the question is, a match is randomly chosen. What is the probability that India have won that match? Okay. So out of 360, we are choosing a random match. It's asking what is the probability that India have won that match. So we have to look at this column, right? And we have to get all the true values, because this is all India data only. There is no different country. This is all basically Indian data. We just have to check the one column. So df 1, let's see, what does this give? This is a convenient Boolean mask, right? So if we get all the list from here, these are all the records where we won the match. Now, what is the probability that India have won that match? So we know the probability formula, right? So it is the favorable outcomes, which is the possible outcomes, which is the outcomes where we won this match. So if we do a length for this, I don't think length will work. Okay, length worked. So all we have to do is length by total number of outcomes, which is nothing but our 360. So we do a df dot shape, or we can do length of df as well. I think that should also, which is 51%, right? 0.51 is nothing but 51%. So the probability that India have won the match is 51% as per this data set. Let's look at the next question. A match is chosen at random. What is the probability that Sachin has scored a century in that match? So this is by default Sachin data anyway. So you see here, this is the century column. We'll have to get the Boolean mask of centuries. What is the probability that Sachin has scored a century in that match? So we'll get all the century matches, right? These are all the things where he scored a century. So you see here all trues. Now again, these are the favorable outcomes. Total number of outcomes is obviously the sample space, which is the entire data set, length of the data set. If you see here, 12% of the times, 12.7, approx 13% of the times, Sachin has scored a century in every match. So in the matches he played in as per this data set. Yeah, this is dummy data set, but Again, we're talking as per the data set. That's how you calculate probability. Then if we look at the next question, let's see, find out how many matches India have won when Sachin has scored a century, and how many matches India have won when Sachin didn't score a century. So there are two ways. So what is it asking? Find out how many matches India won when Sachin scored a century. So both India won and Sachin scored a century, and India have won when he didn't score a century. So we can do this in the traditional way as well, but we can also do this using the contingency table. I don't know if you saw the data visualization class, we discussed about contingency tables there briefly. Data visualization or Pandas class, I think data visualization class. We saw contingency table. We do a crosstab, pd dot, I think df dot crosstab or pd dot crosstab. We'll see. Anyway, if we do this the traditional way, the traditional way would be, we'll have to, one second. Yeah, so the traditional way will be how many matches India have won when Sachin has scored a century. So we'll have to first get, we'll have to do a intersection of these two. So we'll get the matches where India has won first. So DF 1. So these are the India matches. df.log. So these are matches India won. So let's call it India won, and it's just India won dot add 2. Let's keep it this way. Then Sachin has scored a century. Then let's get the century matches. Sachin century would be df log, when we'll pass our mask, which is nothing but the century. We display okay, so these two are the conditions there. So find out how many matches India have won when Sachin has scored a century. So what we have to do is we have to check is in, right? So we'll see, we'll do something like df dot is in no, wait, so df1 India. So we are checking if how many, we are getting a Boolean mask for this one, and we'll do the same for century as well. Century, Sachin 100 century. Find out how many matches India have won and Sachin has scored a century. Is there a easier way? We will discuss about contingency table, but So this will give us our total Boolean mask. Now all we have to do is pass this to the data frame. df.lock and this will give us the list of see, India has won and Sachin has scored the century. True, 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 and true. Right? Now you see here, this is like a ton of steps. I have to write so much code here. This one and this one. Right? And how many matches India have won when Sachin didn't score a century? Again, the same. We have to do similar, like all this tedious process. Right? So in order to avoid writing so much code, we can implement something like you can use contingency table to quickly give us the result. So we can do something like df, is it df.crosstab? Wait, or is it pd.crosstab? I think it's excuse me. It's pd.crosstab. Yeah, it is. So what does it take? It takes index and columns, values. Okay, 1 second. I think yeah. So index will be the so what is it asking? It's asking 1 and century, right? So index will be, what is index? Series or list of arrays or series. Okay, we have to pass the series. Okay, so we can do a df dot index will be df one, let's call it 1, and columns. So the index will be the row indices. So that will give us all the matches 1, and columns we will put it as the century columns. So something like century. And we also want to get the totals. So there is something called margins. If you see the margins here, margins, where is margins? Margins. So margins is a Boolean. It adds the subtotals. So we want the subtotals. So margins true. So if we do this, you will see here, we will conveniently get the totals and the respective scenarios where when the India has won and Sachin has scored a century. So if you see here, all these are pertaining to the 1 scenario and all these are pertaining to the century scenario. So here century is false and 1 is false. There are 160 of them, and the question is asking, find out how many matches India have won and Sachin has scored a century. So 1 should be true and century should also be true. So 30 of them we have scored. We can actually tally that here with this 1 century length of we have exactly 30. See, so all this stunt to get this value, simply we can use this contingency table and right. So this is the scenario where India won and Sachin scored a century. We have 30 out of what? How many matches India have won when Sachin has scored a century? So these are the matches India has won when Sachin scored a century. So if you see the totals here, this is 154 plus 30, 184. This is 160 plus 16, 176. So this is row wise and column wise, and this is the full total. We saw the shape, right? These are the total number of records. So, right, so the question is, how many matches India have won when Sachin has scored a century? So that's 30. And how many matches India have won when Sachin didn't score a century? That is, India have won. So we have to one is true, and didn't score a century is 154. So when Sachin didn't score a century, we won 154 of them. So that's how you so that's how you solve this question. So if we take the, what can we do with this? So if we do a 154, we do a 30 by 360, that is 8%. So Sachin, we won 8% of the time when Sachin scored a century. Which is, so what it says is, I guess, the team was maybe got overconfident or something when Sachin scored a century, and then they relaxed, or they probably slacked off thinking that we will win, and turns out we didn't most of the times, at least as per this data set. So the insight is we will win more if Sachin doesn't, or India will win more if Sachin doesn't score a century. A very counterintuitive insight. And so yeah, that's how you solve these probability questions. Yeah, I hope that was clear, and I'll see you in the next one.